Okay, so in section 5.1, we are looking to add and subtract polynomials. So really what we mean by polynomials is just like terms. Yeah, okay. So in order to kind of talk about when we say like terms, let's kind of define those. So in order to kind of define that, first we need to talk about if we have something with just a bunch of terms, like 8x squared plus 6x plus 9. So right now, these are not like terms, and the reason for that is there are no variables to the same power. So the way we kind of order variables is by their power, also sometimes called the degree of a term. And if it's a single term, we tend to call that monomial. Just say it this way. Degree of a monomial, which is just a single term. It's just the power of the variable. So if we had, the exact same polynomial, 8x squared plus 6x plus 9, this 8x squared would have a degree of 2. This 6x, technically there's a 1 here, so that'd be a degree of 1. And here, the 9 has no variables, so that's going to have a degree of 0. So that's the degree of a monomial. Talk about the degree of a polynomial. Polynomial just means multiple. That's the highest power in a set of terms. So if we look at this exact same expression, 8x squared plus 6x plus 9, individually, they have degrees of 2, 1, and 0, but the entire polynomial itself has a degree of 2. Okay. All right. And then the other thing we talked about is if we look at a single term, let's look at, 12x to the 5th. This number in front is what we call the coefficient. Once again, probably stuff you're all fairly familiar with, just kind of making sure we all have the same vocabulary. And then we have what we call the leading term, which is that highest power term. So something you have in your homework is, let's say you have, 8x to the 4th minus 16x to the 5th plus 12x minus 91. And it says a couple questions, which is what are the individual degree? What is the polynomial degree? What is the leading term? The individual degree is very simple. We're just looking at the powers here. So this is a power of 4. This is a power of 5. This is a power of 1. This is a power of 0. So those are my individual degrees. Polynomial degree is just the highest power here, so that would be 5. And the leading term is that highest power term, so it would be negative 16. Next with it. Okay. Questions about this, anybody?
Professor, would we write for individual degrees, would we write 0, 1, 4, 5?
Yeah, so if you want, you could. We tend to, if you're going to label these, we're going to reorder it. We tend to go from top down. So you would say, all right, negative 16x to the 5th plus 8x to the 4th plus 12x minus 91, if you're going to actually reorder them. But in terms of what the actual individual degrees are, you want to keep them in the same order that your terms are in. So if your terms are in this order, this is how you want to list them out. What you'll actually have is something very similar to this in your homework. You'll have basically a little box connected to the term asking you what each one of them kind of is.
Yeah, thank you.
You're welcome. Alrighty. And then just 2 more little vocabs, what we call a binomial and a trinomial. Is a 2-term polynomial. So, 6x plus 8y. And a trinomial is a 3-term. So 6 plus 8xy plus 9c squared. Okay. All right. And all of these are just more kind of used to like labels as opposed to anything to really do with them. It'll, your homework will say like, oh, add the following 2 binomials. And if you don't know what a binomial is, that question can be kind of confusing. So yeah, these are really just kind of terms to name things. All right. So when we talk about like terms have the same variable, the same. So most common mistake is people, if we have something like x cubed plus 2x squared, we cannot add these two together because here we have a power of 3, here we have a power of x squared of 2. So if you're asked to add them, that's it, that's done, that's simplified. There's nothing else to do with it. The only thing that we could do is if we have something like, x cubed plus 2x cubed. Now we have common terms, so we'll just add the coefficients of 1 plus 2 would give me 3x cubed. So when we're dealing with different powers, we're really just matching up things that have the exact same powers and then just adding the coefficients. And these become a little bit more, they might require a little bit more setup, something like this. Subtract the following. So in this case, we're going to do a little bit of distribution. Since there's nothing being technically, if you want to think there being a positive 1 in front here, but if you are, when they're written like this, we can actually just drop the parentheses of the first term. And then for the second term, we are just going to distribute. So that's going to give me minus 2x cubed. And then minus 2 times minus 4x gives me positive 8x. And now, once again, what I like to do is go down from highest power to lowest power. So we have an x to the fourth, no other x to the fourth, so we just bring that down. Next power down would be our x cubed, so that's going to be minus 2x cubed. And on down, plus 3x squared, plus 8x, minus 2. So in terms of subtracting, there were no actual terms in this example. So really all we're just doing is listing them from in descending order, from the highest point to lowest point. Okay. Questions on that? Anyway. Let's do another one. It's the same thing. I'm going to treat the number in front of here as a -1, and we're just going to distribute. So the first trinomial is just going to come down, x squared plus 3x plus 9. And then distributing is going to give me minus 2x squared plus 8x, so minus 2x squared, plus 8x, and then minus 15. And now we're just going to go through and pair off my like terms. So we have an x squared minus a 2x squared would leave me with a negative x squared. Positive 3x plus 8x leaves me with 11x. And positive 9 minus 15 leaves me with negative 6. So I'm just writing this without all the colors. There's my final subtracted polynomial. Okay, questions on this?
Professor, on the question above that you just did before this one, how did you get minus 2x cubed?
So we had a minus 2 times a 1 cubed. So the negative 2 times the 1 would give me minus 2x cubed.
Oh, okay. Okay, I saw it. Yeah, I'm looking at the next to the x quad. All right, that makes sense now. Thanks.
Okay. Any other questions on this so far? All right. So going back to doing some function notation stuff, let's say we're given f of x. F of x is the polynomial 3x squared plus 4x plus 1. And g of x is the polynomial 8x squared minus 2x minus 1. So we're going to do two things. First, we're going to compute f minus g of negative 2. So what that means is we're going to take f of negative 2 and subtract off g of negative 2. So that just means that we're going to plug in negative 2 into my f. So here's what that looks like. That would be 3 times negative 2 squared plus 4 times negative 2 plus 1. And then from that, we're going to subtract, once again in parentheses, be careful with that, plugging in negative 2 into this expression. So that's going to give me 8 times negative 2 squared minus 2 times negative 2 minus 1. Okay, so now just working this out. So that's going to give me, in parentheses, it's going to give me 3 times 4 plus 4 times negative 2 gives me actually a minus 8 plus 1. So that's 12 minus 8 plus 1, which gives us 5. And actually, at this point, we can kind of just drop the parentheses. We just have the number 5. Then subtracting down, in red, we're going to have 8 times 4. The minus and minus is going to give me a plus 4. And then we have a minus 1. So 8 times 4 is 24. Plus 4 minus 1. So 24 plus 4 is 28 minus 1. So we're going to have minus 27. So now we have 5 minus 27 gives us negative 22. Okay. Here's an example where we're asked to plug in a 2 into the difference of the two polynomial functions. Questions on this? Call this like a part A. Part B, we could ask, what is f minus g of x? So this just says, instead of plugging in a number, we're just going to take f of x minus g of x. So we're going to take our first expression, 3x squared plus 4x plus 1. Then we're going to subtract off our second expression of 8x squared minus 2x minus 1. Excuse me. So just like before, I'm going to treat this as a negative 1, and then I'm just going to distribute. So the first one's just going to come down, so 3x squared plus 4x plus 1. And then now distributing, that's going to give me minus 8x squared plus 2x plus 1. So now just going through and combining our like terms. 3x squared and negative 8x squared will leave me with negative 5x squared. 4x and 2x would leave me with plus 6x. And positive 1 plus positive 1 leaves me with positive 2. So once again, I'm just rewriting it with the colors. We have negative 5x squared plus 6x plus 2. Okay.
Professor, did you put a negative 1 in front of g of x just so that it could turn into positive numbers?
Well, the idea is that we have this, we're subtracting, right? So the way I'm dealing with subtraction is I'm treating this as a negative 1 and then just distributing through that negative 1 on everything. Does that make sense?
Not really.
So, okay, here's the thing. Anytime you have, if you say 6 plus, let's say, a negative 4, you can treat that as 6 minus 4, right? Those are equivalent.
Right.
6 plus a negative 4 is positive 2. 6 minus 4 is positive 2. What I'm doing is I'm taking this and working it backwards. I'm saying that I'm taking this subtraction and I'm treating it as I'm going to kind of add a negative 1 distributed onto those things.
Okay, that makes more sense.
Great. But yeah, the general rule of thumb is what I'm doing is I'm just kind of distributing a minus. And by distributing, we need to multiply by something. And what I'm multiplying by is negative. It's another way to think about it. All right. Any other questions on this? All right, that's it for 5.1. Pretty short section. Next, we're going to look at section 5.2. Okay. So in general, I mean, we've done this a little bit already, but there's something like what is a power, an exponent, right? 2 to the third means just a shortcut. It's a shorthand for repeated multiplication. 2 to the third is 2 times 2 times 2. So if we have something like 2 to the third times 2 squared, well, if we break that out, the first one would be 2 times 2 times 2. The second one would be 2 more. And if we count that out, that would be the equivalent to saying 2 to the fifth power. Now, we can actually calculate what that is, which is 32. But the important thing is kind of the relationship that happens between these terms. Because if we have something, let's say, doesn't simplify, let's say we have, x to the fourth times x cubed. What I want to be able to do is multiply these together to get a common term. And once again, if we pull that trick one more time, if I break this out as x 4 times, and this here is x 3 times, we have in total, feel free to count them up, we have 7 x's. So what we're doing here, equivocally, is multiplication of the exact same term leads to an addition of powers. So this is going to be our first power rule. We're going to have a couple. So in general, if you have something like a to the m times a to the n, it's important that they have the same variable base. But if they have the same variable base, we can just multiply them together by adding the two powers. So if we have something like this, now remembering that multiplication is a commutative operation, which means we can change the order around. Technically, this is 3 times y to the 10th times 8 times y to the 4th. So if we want, we can kind of reorder this to make this a little bit easier to look at. We can say, I'm going to move the 3 and the 8 together, and then y to the 10th times y to the 4th together. We can always reorder multiplication. So 3 times 8 gives me 24, and y to the 10th times y to the 4 leaves me with y to the 15th. Now, this is a little bit more work than you should regularly be doing. Really, the way you can kind of do it is just go down the line. Take all of the numbers multiplied across, take all the variables multiplied across. Be careful, we're not doing distribution. A common mistake students will do is like, oh, okay, we'll do the 3 times the 8 and 3 times the 4. You only do a distribution when you have addition and subtraction. Here, all we have is multiplication. That's the only operation we're doing here. So because of that, we're only going to multiply the terms with another one. Okay. So Once again, we're just going to go down the line and multiply. First, we have our coefficient of -4 times 5 gives me -20. Then we have our x terms. We have x squared times x to the, careful, remember that there's always that, we don't write it, there's an assumed power of 1 there. So adding that, 2 plus 1 is going to give me x cubed. And then lastly, y cubed, y to the 5th, add those powers together to give me y to the 8th. Okay. Questions on this? I want to talk very quickly about the difference between, and there is actually a difference between -4 squared and parentheses -4 squared. And this really just comes up when we're plugging in and doing this sort of stuff. But we need to be careful here. This here represents -4 times -4. Because the order of operations is we're taking this parentheses and square it. So that's going to give me +16. What this technically represents is -4 times 4, which would technically give me -16. And this is more a notational difference than it is anything else. But if it's not in parentheses, you do the exponent part first and then apply the negative symbol. And really, the only time this is going to come up is when you're dealing with this type of stuff in like a calculator, and just kind of talking about that real quick. That's not what I want. Okay, there we go. So if you have something like, once again, you can double check it's -4 squared. Calculator says -16 as opposed to parentheses -4 squared +16. So just be careful about that, especially when we're doing plugging into like, squares and whatnot, about the difference between those. Technically, anytime you plug in, you're always plugging in as a parenthesis. Okay. All right then. Any questions on that?
So for the one on the
with
left,
regards to the first -4 to the second power, the second power only applies to the number 4, not the negative sign?
So the thing is that if I wanted to imply to the negative, I have to put that in parentheses.
Okay.
So here, the 2 is, you can kind of look at this one. We're kind of treating this as a 4 squared with a negative in front. That's how it's being treated. We don't write it that way per se, but when we write it like this, we're saying do the exponent part first and then apply the negative after the fact. If I want you to actually include the negative in your squaring, I'll have to put parentheses around it.
Okay.
Does that make sense?
Yes.
Okay.
Got it.
Is there another question?
That's it.
All right, so let's talk about two. So there are kind of two weird things, which is we're going to talk about what happens when powers are 0 and negative numbers. But in order to kind of do that, first let's just kind of talk about some regular powers. So let's say 3 to the 1 is 3. 3 squared. What's 3 times 3, which is 9. 3 cubed is 3 times 3 times 3, which is 27. And what we're doing is we're increasing the power by 1 as we go. And so what we're kind of doing as we move here up on the right-hand side is we're basically adding another 3 here, right? This here is just a single 3. This here comes from 3 times 3. This here comes from 3 times 3 times 3. So all we're doing is we keep multiplying through by 3. So one thing you can kind of look at is instead of doing each one of these individually, I could say, all right, well, all I'm doing is taking this term here and multiplying that by one more 3. 3 times 3 gives me 9. If I multiply by 3 again, 3 times 9 gives me 27. When we go to 3 to the 4th, 3, we multiply by 3 again, 3 times 27 gives us, double check with your calculator, but 81. So as we move up through here, we're basically doing multiplication. So if we go in the reverse direction, if we start going down, we could say, well, as I move down, we're losing a factor of 3. So I'm dividing by 3. 81 divided by 3 is 27. As we move down a row, 27 divided by 9 is, sorry, 27 divided by 3 is 9 divided by 3 is 3. So if I go down one more level, this would be 3 divided by 3, which would just leave me with. And what we're doing here is we're counting down the powers. So 4, 3, 2, 1. The next power down would be 3 to the 0. And this is actually going to be our definition for what a 0th power is. Three to the 0 is defined to be 1. And this actually works for any number. 4 to the 0 is also 1. 10 to the 0 is also 1. The only number, so in general, anytime you have a 0th power, this is going to be another power rule for us. X to any power of 0, if any, sorry, it's another way. Any base of x to a power of 0 equals 1, so long as x does not equal 0. Because we defined this operation on division, remember that dividing and 0 don't work well together. So this is what happens whenever we go for 0, anything to 0 power is 1, unless it's 0. General rule of thumb is if it's 0 to the 0, that's going to be undefined. Okay, so I'm going to go down one more level. We had 4, 3, 2, 1, 0. The next one would be 3 to the negative 1. And if I divided that by 3 again, well, that'd be 1 divided by 3, or just 1/3. And we can kind of keep going. 3 to the negative 2, if we divide that by 3, that would leave me with 1/9. And we're starting to see a pattern here. Basically, this number here is the same as this number here, just as reciprocal. This number here is the same as this number here, except as a reciprocal. So we can kind of go through 3 to the negative 3, 3 to the negative 4. Without even kind of doing the math, we can say 3 to the negative 3 is just 1 over 27. 3 to the negative 4 is 1 over 81. And we kind of have this pairing here, which is that anytime you have a negative power, the negative power and the positive power are just reciprocals of one another. So that's going to be our next power. How do we deal with negative powers? Well, if we have, let's make sure, yeah, your book uses x here. X to the negative n, the way we could write that is 1 over x to the positive n. So we reciprocate it, and then we flip the sign. The negative sign now becomes a positive sign. So just a note, all of these numbers, these are all positive numbers. A negative power does not cause a negative number. Because remember, powers means that we're just dealing with multiplying and dividing positive 3. And if I'm only ever multiplying or dividing a positive number in there, there's no way to get a negative out. So it does not affect the actual sign, whether it's positive or negative. It affects whether or not that should be in the numerator or denominator. That's what a negative power does. It's basically a reciprocal power. Okay, so these are kind of our two new power rules, which is a 0 power and a negative. So, you do have a couple things where you're asked to evaluate, what is 5 to the negative 3. So the simple answer here is we're just going to write this as 1 over 5 to the positive 3. And then just simplify what is 5 cubed. So this is going to be 1 over 100. We can also talk about fractions and numbers. If we have something like 4/5 squared, what we can do is, remember, to do everything squared, multiply it by itself. What this becomes is 4 squared over 5 squared, because it's 4 times 4 over 5 times 5. So anytime you have two terms to some power, we can always write that as that power over b, that power. If we have a fraction, to a negative power. Well, the easiest way to do this is remember that negative powers cause reciprocals. So what I can do is just take a reciprocal of this to be 3/2, and now we can raise that to a power positive. And now applying this last rule we just wrote down, this is 3 to the 4th all over 2 to the 4th. 3 to the 4th power is 81. 2 to the 4th is 16. Okay, question on this, anybody?
Professor, on the 16, do you want us to break it down even more or just leave it as is?
Well, actually, as it turns out, because we couldn't break this down, right? We couldn't break this down at all. So because of that, we actually can't break this down. 81 and 16 will not have any like terms, because this is just, remember, 3 to the 4th is 3 times 3 times 3 times 3 over 2 times 2 times 2 times 2. None of these will cancel out. So that means that 81 and 16, that is a simplified fraction. Or were you talking about like mixed fraction or something like that?
I was kind of talking about the 16/25 as well.
Oh, same thing, right?
Yeah.
4 and 5 have no common factors, right? So because of that, this is 4 over, 4 twice, 5 twice. There's nothing to simplify here, which means that there's nothing to simplify here.
Okay, got it.
If there was, and once again, we can kind of talk about that. If there was, let's say we had something like 3 over 9 squared. There are kind of two ways you'd work this out. You could simplify it before you hit the power or simplify it after you hit the power. So here, if you simplify it before, that would be 1/3 squared, which would be 1 squared over 3 squared, which is 1/9. Or you could square it first, so say that's 3 squared over 9 squared, which is 9 over 81, and then simplify it after the fact. You get the same value either way, 1/9. I think it's usually a little bit easier to simplify before you hit it with the power. But the general rule of thumb is if the fraction is simplified before you hit it with the power, the fraction you'll end up with will already be simplified. There's no simplification to do.
Okay, got it.
All right. So speaking of fractions, yeah, let's see. Do a couple. We did that one. Oh yeah, one thing I want to talk about with negative powers. We have something like this. So be careful, kind of going back to the talk we had with negative numbers and powers, coefficients and powers, you also have to be careful. Technically speaking, this is 3 times x to the negative 5, because the power is only on the x. So the way we'd write this is 3 over x to the 5th. If we wanted to bring that 3 into the denominator, what we would have to do is write it as 3x to the negative 5. And then this would become 1 over, and then now we'd have to actually say, all right, well, this is 3x parentheses to the 5th. And then we'd have to kind of work this out, right? That's 1 over 3 to the 5th is, I can't do 3 to the 5th. 243 x to the 5th. Okay. Yeah, so just be careful when you have negatives, that you only apply the negative power to the variable it's attached to. If there's a coefficient, the only way we apply the power is if it's in a parenthesis with the variable. Okay. This actually brought up something else, which is what happens when we have something like this. What happens when we have both a coefficient and a variable to a power? And the answer is that we can just both of these out separately, kind of like distributing the power. We can write this as a 2 cubed times a x cubed. 2 cubed here is 8. And x cubed is just x cubed. There's no simplifying x cubed. So general thumb, if you have a times b to some power n, we can write that as a to the n times b to the n. All right. All right, so let's look at division. So like we said, if we have something like x to the 5th times x squared, we add the powers together to give us x to the 7th. What we now want to look at is what happens if we have something like x to the 5th divided by x squared. So once again, if we write this out in long form, that's x times x times x times x times x. There's 5 of them there, and we're dividing that out by x squared, so that's 2 of them. And anytime you have the same thing on the top and bottom of the fraction, you can cancel it out. So what we have now is we're left with 3x's up top, so that's a x cubed. So if we look at here, what we're doing here is when we do division, we end up subtracting the powers. So if we have something like, x to the 15th over x to the 3rd, we can simplify that out. 15 minus 3 would leave us with x to the 12th. So, yeah. So the power rule, it says that if we have division, so actually we have a to the m over a to the n. Power rule here says you subtract those 2 powers. All right. So we could have something once again, like let's say we have something like this, 3 x cubed over 12x to the 5th. So what you want to do is 3 and 12 are not powers, so we're not going to treat them as powers. We're going to treat them as a fraction, right? If I had 3 over 12 by itself, I could simplify that down to be 1 over 4. So that's what I'm going to do, 1 over 4. Now, there are kind of 2 ways, actually, let me write it like this. Let me just write this forth right now. There are 2 ways you can deal with this. You could treat it quite literally. This is 3 minus 5, which is negative 2. So you say this is 1/4 x to the negative 2. That's one way to write it. The other way is doing what we did with negative powers of 1 over 4 and then times 1 over x to the positive 2. So it would leave us with 1 over 4x squared. Both of these answers are valid. Sometimes on your homework or an exam, you'll ask to write it with positive powers only. And we tend to lean towards this one, but like I said, there are times when we do actually want the negative powers there. If the homework doesn't say, the homework will take either one of these. But there are homework problems where it does ask you to leave your final answer using, oops, not what I wanted. To leave your final answer using only positive powers. So just be aware. Okay. Let's do one more of these hundreds. Okay, so what I'm going to do is just going down the line. 9 divided by 3. The rule of thumb is whichever one's bigger, that's where the result's going to end up. So we have 9 over 3. Well, that's a 3, and the 9 is bigger, so that 3 is going to go up top. Now, technically speaking, if we have x squared over x to the 4th, if we subtract that, that would leave me with x to the negative 2, or 1 over x squared. The way I like to think about this, and the way to simplify it, especially when you have all these variables here, is first subtract them. And then the result is just going to stay with whichever term had the bigger power. So 2 minus 4, that's 2. And because the x to the 4th is bigger, the result is going to stay in the denominator as a positive number. And then lastly, we have y to the 5th over y squared. Subtract that out, that's going to give me 3. And what we have left over is the 5 is bigger, so that's going to be a y cubed up top. So then just kind of rewriting it so it looks normal. So do 3y cubed all over x squared. Okay. Questions on this example, anybody?
So, Professor, just as an example, let's just say it was a y2 minus y5, which would equal -3. Then would we put that y negative cubed down below next to the x squared?
So in this example, if you had a y squared over y to the 5th, that would be, technically, if you divide it out, that'd be y to the -3 or 1 over y cubed.
Right.
So yeah, if these were flipped, you switch the 2 here with the 5 here, that would say now the 5 is bigger, so now you'd have y cubed in the denominator.
Okay, cool.
But note, since the 5 is bigger, it's going to stay positive in the numerator. If it was in the numerator, it'd be negative. That's kind of something you can always do with just flipping back and forth. We can always flip back and forth. It just costs us a sign flip. Does that make sense?
Yeah, yeah.
Great. Go back to the original problem. That. Okay, cool. Great. Okay, one last power rule, and then we'll bring this all together with one big example and an application of it. So let's talk about what happens if we have x squared to the 3rd power. What happens when we raise a power to a power? So once again, writing this out in full. Well, this says we're going to take everything in the parentheses and write it out 3 times, right? So this would be x squared times x squared times x squared. So what that happens is, well, multiplication means we add the powers together. So 2 plus 2 plus 2 would leave me with x to the 6th. So what we did here is we took 2 and 3 and got a 6 out of that. That's technically a multiplication operation. and it's going to be our last power, which is anytime you have 4 raised to another power. The way you simplify that is you just multiply the 2 powers together. So if we did have something like, let's say, 3x squared to the 4th power. Do be careful. That power needs to hit everything inside. So first we're going to have a 3 to the 4th, and then x squared times x raised to a power of 4. We take the 2 times the 4 to give me x to the 8. And then we'll simplify this. 3 to the 4th gives me 81x to the 8. Okay. Questions on this example? Anybody? All right, let's throw all of this together in one very big example. All right, this is pretty much going to have all of our power rules in one big. So kind of talking about how we did before, what I like to do is before I deal with powers, I like to simplify everything. But remembering that negative powers cause reciprocals, my first step here is I'm going to make that positive 2 power by doing the reciprocal fraction. So it's going to be 16 xy to the 5th, 4x y cubed. X squared y cubed. So now we have a positive 2 there, but before I apply that 2, what I want to do is go through and simplify each one of these. So 16 over 4, that's going to leave me with a 4, and since the 16 is bigger, it's going to be up top. Remembering if there's a 1 here, 1 minus 2 is it's going to be in the denominator, so technically that's an x to the 1st. Technically you don't have to write that, but I will just so people don't get confused. And then we have y to the 5th over y cubed. Subtracting that out will leave me a y squared, and it's going to be on top because 5 is bigger. Okay. So my last step is I'm just going to apply this 2 to all 3 terms. So first we have 4 squared, which is 16. Y to the 2 raised to the power of 2, we multiply that together to give me y to the 4th. And then x to the 1st times x to the 1st raised to a power of 2, 1 times 2 would leave me with x squared. So there is my fully simplified expression. Questions on this example, anybody?
Why is it not x cubed then x squared?
So we're taking, this is technically x to the 1st power raised to the 2nd. When we do a power to a power, we multiply, and 2 times 1 is 2. That's why it's not x cubed.
Oh, okay, I see.
If that had been x to the 1st times x squared, that's where you would have added them to get x cubed.
All right, I got it.
Great. Great. Any other questions on this? All right, so the actual application of this and where you'll see this in your other classes is in what's called scientific notation. And really, scientific notation comes from dealing with something that are really, really big and really, really small. So in both cases here, the only numbers that really matter here are the 6 and the 3. All the zeros do is these zeros tell me that the number is a really big number. These numbers here tell me that the number is a really small number. So what we're going to do is scientific notation says we're going to get rid of all of this kind of necessary zero information. And the way we do that is, in general, scientific notation is always of the form some number, we call it capital N times 10 to a power. And N here is always between 1 and 2. So what this translates to is you want one number in front of the decimal. So for this first example, the decimal's right here. And if we count it out, I'm moving it 3, 6, 7. That's 8 decimal movements. So I can rewrite this as 6.3 times 10 to the 8th. So we're taking this whole big thing and contracting it down to a much, much more compact number. Likewise, here on the bottom, kind of erase this bit. If we count this out, we want the decimal place to be in between the 6 and the 3, so that's 2, 3, 4, 5, 6, 7 decimal places. But since this is a small number, this is going to be 6.3 times 10 to the negative 7. So this is basic scientific notation, which is basically we're dropping off these zeros and really just boiling it down to what's the important measurement. And then in terms of bigness or smallness, well, we'll just let it, if it's a positive power, that means it's a big number. And if it's a negative power, that means that it's a small. Okay. Question on this so far? All right, so kind of going through this a couple ways, just you have a couple of these where it's like, okay, you've got something like, turn this into scientific notation or turn that to scientific notation. So just kind of working these out. Once again, starting off with the decimal place right here. That's 3, 6, 9. And then that would put the decimal right here, which is where I want it. So that would be 4.7 times 10 to the 9. This example, if we count it out, here's where we want the decimal place to be, one number in front. So we just count it out, 1, 2, 3, 5, 6, 7, 8. So this will be 7.14 times 10 to the 8th power. Now, what's nice about this is actually is very, very easy to do multiplication on. If it's in this scientific notation form, we can actually do multiplication very easy. Let's say we have something like, 1.9 times 10 to the 12th, and we're multiplying this times 1.75 times 10 to the 15th. These are both really, really huge numbers, and they look really messy. But in terms of the actual multiplication, it's actually very, very straightforward, because we can just throw this into a calculator 1.9 times 1.75 gives us 3.325 times 10. And then if we look here, we have 10 to the 12th times 10 to the 15th. And since we're multiplying, that means we just add the two powers together. So 12 plus 15 would just be 10 to the 27. When it's in the scientific notation form, these are very, very easy numbers to multiply out. One thing we do have to keep track of is every now and again, we'll have an issue where we change where the decimal place is. So let's do an example of that. Let's say you had something like 4.25 times 10 to the 5th. And we'll multiply this times 6.81 times 10 to the 7th. So when we do our first multiplication, 4.25 times 6.81 gives us 28.9425. We'll deal with this in a second. Dealing with the numbers here, it's going to be times 10 to the 12. Now, when we're doing scientific notation, we only want one number in front of the decimal. So I need to move this number over 1 to make it 2.89425. But since this is a bigger number than what I have here, that means I need to add 1 to the power. So you have a couple of these where you'll do your multiplication and you'll be left with something that has more than one number in front of the decimal place. That's fine. You just move the decimal over and change the power accordingly. Okay. Let's do one more of these. Let's talk about division. Oops, wrong way. Times 10 to the 6. So once again, in terms of dividing, first you're going to do the first bit. We're going to take 1.25 divided by 2.5, which leaves you with 0.5. And then remember that we're subtracting here. So this is 5 minus negative 6, which would leave me with 11. Let's put that. Five minus negative 6, which would leave me with 11. So that'll be times 10 to the power of 11. Once again, we have the decimals not in the right place. I want it to be in front of, I want it to be behind the 5. Right now it's in front of the 5, so I need to move it over 1. But that was a smaller number, so that means that I need to subtract 1 from this paper. Technically, if you want, we could say that this is, if you want a decimal here, 5 point. Questions on that, anybody? All right, well, that's going to do it for today. There's 5.1 and 5.2.